Krishna Rao. And now Professor Jennings will introduce the speaker.
I don't really know how to talk into the owl and at the camera, but I'll do my best. So I just wanted to introduce Krishna Rao, my great honor here. Krishna got his bachelor's in civil engineering from ITT Madras, where I recently discovered that he was first in his class in his department. American there. He then came to Stanford a few years later to do a master's in the civil engineering department. And we were lucky enough that he wanted to do a side job in our group and in our system science, and then we're able to recruit him to stick around for the PhD. It's kind of hard to stay brief in summarizing how great it's been to have Krishna in the group. So I'm just going to do it nerd style and just mention it in the numbers. So he's had 7 papers with the group so far just yet, 2 more that I expect to be added soon, 170 citations, and a helpful new, more than 170 helpful new public data set. But he's gone much beyond the numbers. He's taught the group so much technically, things like how to use Git better, all kinds of tricks for visualization, how to participate and win in hackathons. He has then actually scaled those teachings to not just a group, but to Stanford and even beyond. I've heard from people totally unrelated to Stanford that they've seen Krishna's articles from when he was a Stanford data science scholar. And then, I just want to say it's been really great to have him in the group, not just technically, but also because he's been incredibly supportive in all kinds of big and small ways, encouraging, but also really just encouraging people not to be their best technical selves, but to always have fun and stay enthused. And that's just totally, not measurable. So I will let Krishna introduce his research. He's off, just as the last piece of info, he's off next to Watershed to help companies figure out, count for their carbon footprint. So they're lucky to have him. And I hope you enjoy the talk.
Thank you. Let's get started. Before I begin with the talk, I'd first like to mention that before, apart from the people here and on Zoom, there's going to be one other attendee, and their name is Dante, the disinterested dog. Dante is going to be very disinterested in my research, and it's going to be up to me to keep Dante interested, but it's going to be up to all of us to keep Dante impressed and excited about this talk by showing all this positive energy and excitement. Topic of my research is understanding tree mortality and wildfires with microwave remote sensing of vegetation water stress. I know that is a mouthful, but we will take one step at a time and understand term by term, starting with what is vegetation water stress. Vegetation water stress is a physiological condition in the vegetation when water demand exceeds water supply. Here, 2 of the biggest water fluxes in a plant is shown. The roots take in groundwater from the soil. The xylem transports the water through the trunk, and the leaves transpire the water out into the atmosphere. But when there is more atmospheric demand for that water, the efflux of water can exceed the influx, leading to water stress in the median. But if you're already bored like Dante and thinking, why should we care about this vegetation water stress? Well, I'm going to make a big claim that understanding vegetation water stress is critical to understand the Earth system. Here, various different effects of droughts and vegetation water stress is shown. I don't want you to go through all of them, but just highlighting 2 key aspects of why we should care about vegetation water stress. Here on the left side, you can see that vegetation water stress can lead to wildfires, which can then turn air quality poor, like we experienced in California in the last 2 years during the summers. Vegetation water stress can also limit the amount of carbon dioxide sequestered because stressed vegetation can reduce the amount of carbon dioxide assimilated in the leaf. But how does this actually work? Let's again zoom into one tree, and there is roots, xylems, and leaves, as I mentioned earlier. But if there is vegetation water stress, small bubbles can get introduced into these conduits called xylem. And these bubbles occur because of this intense negative pressure. The xylem is trying to suck water from the ground, but there is not enough water to meet that demand, right? And these bubbles are the same like when you drink from a soda can or boba at the bottom, and if you're sucking intensely, in the end, it can create this sound like, you know what I'm talking about? That's the same bubbles which are occurring, but in the plant conduits called xylem. And even though it just gives some sound and entertainment while we drink from our can, it can actually cause tissue failure and rupture of the xylem when the bubbles burst inside the xylem. And if enough of these xylems fail hydraulically, it can lead to drought-driven tree mortality because there is not enough conduits to supply the water that the plant needs for its physiological well-being. Another effect of vegetation water stress is that stressed vegetation has less water, and if it has less water, it means it's drier, and if it's drier, it can act as fuels for wildfires. Now, these are only two consequences of vegetation water stress. There are more consequences which affect the Earth system, but these are the only two which I'm going to focus on during the thesis. So until now, we have learned that what is vegetation water stress and why it is important to study vegetation water stress. But there's another reason to study vegetation water stress, and it is that it may be worsening. Its condition may be worsening, and globally. Here is a map of drought-driven tree mortality observations by Hammond et al. You can see that the dots are the observed mortality of trees because of vegetation water stress. You can see that there are more bright colors here than dark colors, which means over the last 50 years, there is, in the recent past, there has been more vegetation water stress related mortality than in the past. And not just that it has been accelerating in the past, it might accelerate in the future as well. Here, I'm showing a time series of vapor pressure deficit anomaly. If you don't know what that means, think about it as drier air. And projections from climate models show that in the Western United States, dryness is expected to increase. And this may make vegetation water stress worse in the future. So we saw that vegetation water stress is important, and we saw that vegetation water stress might worsen in the future. But if you're still not convinced and thinking like, oh, everybody has problems, why should we focus on only this problem? Well, this problem is not just important, it's also very hard to measure. Current evidence, current observations of vegetation water stress are only at a stand scale, and I'll explain why that is hard to measure. If traditionally, whenever someone wants to measure vegetation water stress, what they would do is they would go in the field, pluck a small sample of the vegetation, either the leaf or the needles or some thin twigs, weigh it right there at the field, come back to the laboratory, dry it for 24 hours, and then weigh it again. Now, the difference between these two masses will give the amount of water in that component of the vegetation. And this is not vegetation water stress yet, because this is just the amount of vegetation water. If I had put 2 pieces of leaves, then there would be twice the amount of vegetation water, right? So we need to normalize this by some amount. And in the plant physiological community, and ecologists normalize it in 2 different ways. One is normalize it by turgid water, or the maximum amount of holdable water by a plant. So there's a number between 0 and 100 in terms of percentages. Or they divide it by dry biomass as well, which is the final mass from here. And that is also, again, a percentage quantity. The actual name, relative water content and light fuel moisture content, is not that important, but I hope you understand that both are vegetation water stress. They're just normalized by different quantities. Now, this way of measuring vegetation water stress requires us to go to the field every time, and it is very cumbersome. Another way that people have creatively designed is to measure the water potential in the xylem itself. So what this entails is drilling a small hole into the bark such that the xylem is exposed, the conduits which transport that water. And by adding a stethoscope-like device, we can measure what is the negative pressure in that xylem, which then tells how much vegetation water stress is there. Here, for example, if I show the time series of xylem water potential, you can see that there is a strong diurnal cycle related to the water stress in the vegetation between differences in water stress in the vegetation between day and night. And this, although is automatic, it is still cumbersome because every tree, if you want to measure, you have to install this in every single tree. And I know this because I did this field work and I know how cumbersome that is. But again, this xylem water potential and the earlier shown relative water content are monotonically related, which is something that we showed in a review paper. And this all again boils down to the simple concept that all of these different metrics, xylem water potential, relative water content, and live field moisture content are similar and all indicate vegetation water stress. Okay. So we saw why vegetation water stress is hard to measure. Now we'll see why vegetation water stress is hard to scale. One might imagine that if we just measure a few plants and then try to scale it globally, that might work. But unfortunately, it doesn't. And I'll explain it to you why. Imagine there are two trees, one with deep roots and one with shallow roots, as an example. And if there is dry air, the same meteorological conditions for both of these trees, the tree with deep roots will have more access to water, meaning it will be less stressed than the tree with the shallow root, right? Now, this is just an example with root as the varying factor, but other plant hydraulic traits like stomatal control, xylem structure, and the soil characteristics can also influence this vegetation water stress. So just by looking at climate, which is relatively easier to measure, we cannot estimate vegetation water stress because of these inter-trait or interspecies related variants of the plant hydraulic machinery. This is not just a conceptual diagram. I, in fact, also saw an image related to this on a bike ride in Yosemite with the triathlon team, many of who are here. This is an image from a few years ago on Tioga Pass Road, and you can see that after a wildfire, some trees are completely burned here in black, some are just a little bit parched, and some are bright green and healthy. Okay. Again, this is just an anecdote. I don't want you to think that Krishna goes on bicycle and figures out nature. This is also backed by literature evidence. Here, Nolan et al. Show that for the same meteorological conditions on the x-axis, vegetation water stress can have a 6-fold variation depending on which species we are measuring. Okay, and this affects us not just based on how the different plants respond, but it also has very real effects on human lives. One of which is fire danger that I mentioned earlier. Here is a picture that I took near Sequoia National Park at the entrance, and you can see that Smokey Bear is here, and Smokey Bear says that fire danger was low on that day. This low can also be medium, high, extreme. If you have gone to a national park, you might have seen this. But just to get to this adjective rating of fire danger, the USFS uses a model based on many different metrics, including vegetation water stress or live fuel moisture. But live fuel moisture in that model is estimated from meteorological metrics alone. And hopefully by you, all of you, like your eyebrows should raise now. You know that this is not perfect. In fact, people also know that this is not perfect. There are errors in this assumption of link between live fuel moisture and weather, but that is the best we can do as of now, because there's no easy way to scale vegetation water stress measurements globally. So what can we do? Coming back to the same picture, how do we get from stand scale measurements of vegetation water stress to answering all of these important questions and getting a global scale understanding of vegetation water stress. If you're like Dante, you might just give up and go and sleep. But there is one other way we can do this, and that is using microwave remote sensing. If you don't know what's microwave remote sensing, no worries at all. We'll be learning that together. Microwave remote sensing is a way of measuring from satellites the microwave spectrum of either black body or active radiation. So what this means is that there is one kind of microwave remote sensing called radiometers, where we analyze how much of the black body emission from Earth is received on the satellite. Now, black body emission of the Earth is purely because of its temperature. It's at about 287 Kelvin on average, and any body above 0 Kelvin emits radiation. At 287 Kelvin, it happens to be in the microwave spectrum. And when these microwaves pass through stressed vegetation versus unstressed vegetation, because of the high dielectric constant of water, the microwave gets attenuated. So here you can see that the amplitude through this less stressed tree is lesser than the amplitude through the more stressed one. Right? So this is directly a function of the amount of water in the medium that the microwave propagated. This has one downside, that the microwave radiation from the surface of Earth is very weak. The signal is very weak. So in order to actually make observations and have sensitivity enough to estimate vegetation water stress, we need to aggregate over very large areas. One way people have been able to overcome that is by emitting your own microwaves. So there are a few other satellites called radars, which emit their own microwaves and then receive it back, the scattering back. And by seeing how much of the microwaves made it back to that antenna, we can estimate how much of vegetation water is there in that medium. Now, I made it seem very simple, like just by looking at the microwave observations, we can tell how much is the vegetation water stress. But if it was that simple, we would have already been done by now. I wouldn't have to spend years on this problem. The problem is that canopy structure has a huge effect on the observations of microwaves here. So it's not just that the vegetation water affects the microwave observations, but the structure of the canopy also affects the microwave observations. And in my thesis, I have tried to overcome this effect or account for this effect of canopy structure and estimate vegetation water stress and its links to tree mortality and wildfire hazard using microwave remote sensing. My thesis spans across scales and across the scientific process of generating the data that we're interested in to answering or testing the hypothesis that we are interested in. Chapter 1 will focus on a new ground-based radar monitoring system for vegetation water stress. Chapter 2 will focus on understanding the effects of vegetation water stress on tree mortality. Chapter 3 will focus on high-resolution maps of vegetation water stress. Basically, how do we make these maps of vegetation water stress? And chapters 4 and 5 I will investigate the effects of vegetation water stress on wildfire occurrence and wildfire burned area. Okay. Just a minute. All right, so now everybody has the background necessary to understand the importance of vegetation water stress, and you understand how we are able to estimate vegetation water stress using microwave remote sensing. In the last 20 minutes, whatever you learned, it took me a few years to learn that. Good job. Let's get started with chapter 1, ground-based radar monitoring system. The motivation, as I mentioned earlier, is that a rapid plot-scale measurement device for vegetation water stress is non-existent. Right now, we have to measure every single tree. The hypothesis here is that side-facing radar is sensitive to whole plant water relations and whole plant water stress, and this might be cheaper than other existing devices as of now. So before we get from a stand scale measurement to global measurement, we first need to make sure that the stand scale measurement can at least be scaled to the footprint of a satellite observation, right? Because only then we can take the satellite observations and take it globally. But what would we have to do as of now? As of now, let's say this is a 100 meter by 100 meter plot of vegetation. If we have to ground truth or get a measurement related to that satellite footprint, we'll have to measure every single tree here by installing those Xylem water potential meters. Instead, my hypothesis is that if I install the same kind of a radar, but on either side of this transect, there's a receiver there which emits microwaves here. That's a transmitter there, and the receiver gets these microwaves. And if I'm able to estimate the vegetation water stress of this entire transect from the radar amplitude here, then it's low cost as well as rapid in that I don't have to actually estimate every single tree. So this is exactly what I did at Jasper Ridge. Here is an aerial view of that same plot with 3 cyclometers acting as the ground truth. These are the same instruments that I showed earlier. We drill a small hole and measure the water potential. And once I do install these, I go outside of that square piece of that piece of land and then monitor the radars, the receiver. And yeah, there are masks on because you can understand what timeline this follows. Okay, so if my hypothesis is true, that radar amplitude is related to Xylem water potential, I expect a strong relationship between these two, but with a small intercept or small bias because there are like actual biomass effects as well on this received amplitude. But as all things, reality is often not the same as expectations. The actual data showed that although there is a sensitivity to Xylem water potential, there were sometimes huge jumps in the absolute levels of the radar amplitude. And I hypothesize that this is because of internal hardware noise or anthropogenic noise. And my hypothesis is driven by the fact that here, if you see, there are more dark colors. Dark colors are indicating nighttime. And during nighttime, in this same spectrum of microwave, there are others also using the same spectrum, like ham radio enthusiasts, and their signals might be interfering with mine. So there's more work to be done to actually resolve this noise, but I've hopefully showed you that there is a proof of concept here to estimate vegetation water stress rapidly at low cost for an entire plot. Okay, and the second implication for this is slightly personal, is that fieldwork can be a lot of fun. I had so much fun doing all of this work with Yesenia, Nona, Nathan, Nicole, and Greg. And no matter how much time I spend in front of the computer, I think this project will always be my favorite. So coming to the second chapter now, effects of vegetation water stress on tree mortality. The motivation for this chapter is that a species independent indicator of vegetation water stress doesn't exist. We already saw this during the introduction. And the hypothesis here is that microwave radiometry, that passive microwave remote sensing system, can estimate vegetation water stress and predict drought-driven tree mortality. Thankfully, there are observations to support or test this hypothesis. California, actually not thankfully, unfortunately, California went through a big drought-driven tree mortality event from 2009 to 2015, where the USDA predicts that 100 million trees had died, mostly due to drought-driven tree mortality, and that is shown over here. So you see, this is Sierra Nevada, this is Sierra Nevada, yeah, and you can see that dark colors mean higher mortality here. I don't have the time to go into the actual details of how I estimated the vegetation water stress using microwave remote sensing for this chapter, but the status quo until then was that you might know that climate-related metrics were used to capture vegetation water stress. So here on the x-axis is variance explained, and the y-axis is the different metrics which are correlated to mortality, but you can see that they are pretty weakly correlated. And when I estimated vegetation water stress using the microwave satellites, I showed that it was had twice more explanatory power than any other previously existing metric, which is really promising for passive microwave remote sensing as a tool to estimate drought-driven tree mortality. But if you're wondering, like Dante, if I am able to do this at high resolution or like what resolution, unfortunately, the reviewer also turned out to be like Dante, and they gave me a really hard time, saying that one major limitation of this work is that it is at a poor resolution, sorry. Even though I don't like to admit it, the reviewer is right. Mortality occurs at a stand scale, like one tree at a time, right? So that's about a few meters wide. Whereas my estimate in this chapter was for a 25 kilometer by 25 kilometer square. So I'm at a wholly different scale estimating vegetation water stress, whereas the mortality is occurring at a stand scale. And even though this paper on this journal did not get accepted, it inspired me to create high resolution maps of vegetation water stress, which is the topic of my chapter 3. The motivation for this chapter, it's similar, like large scale maps of vegetation water stress do not exist as of now. Only like climate related or meteorological maps are available. And the hypothesis here is that synthetic aperture radar, it's a radar, meaning it might have higher resolution, can estimate vegetation water stress at high resolution. And to again summarize how this works, we know that microwave scattering in the active microwave radar is sensitive to vegetation water. We also know that optical reflectance or infrared reflection, this is just the red, green, and blue colors of a plant. That is indicative of how much biomass is there in that medium. And if you divide these two, I think this should already ring some bells. This is vegetation water stress, specifically live fuel moisture content, right? But then these arrows, as we already know, they are not just like a one-to-one relationship. They depend on canopy structure, and they are highly nonlinear. It's not a single relationship. It's not a linear relationship. There's like some exponents and some other things going on in the physical model of that relationship. So to overcome these two challenges, I use the physics-guided neural network to take in microwave and optical satellite data and estimate live fuel moisture content. But an empirical model like that is only as good as the data which is available to train it. And I was so lucky that the US Forest Service has already been collecting these live fuel moisture content samples, the same images that I showed earlier, all across the Western US, thousands of times. And this project wouldn't have been possible without the painstaking efforts of these scientists for recording this and also making it publicly available for people like me to use. So what this physics-guided neural network is able to do is take these point measurements of vegetation water stress, train on them, cross-validate, and go from these point measurements to continuous time-varying estimates of vegetation water stress. Here is that map for one seasonal cycle I'm showing here, and it is at about 250 meter resolution. So it's 2 orders of magnitude higher than what I showed in chapter 2. And if you think like Dante, and if you only believe what you see, we have made many apps and tutorials and databases and ML training data sets in the Stack database for people to actually use these data of vegetation water stress and also improve the estimation algorithm for vegetation water stress. That brings me to the end of this chapter, where we are able to estimate vegetation water stress at a wide area with very different species. And as of today, it's the most accurate vegetation water stress data out there. So the implications for this chapter is that we have these maps of vegetation water stress, and this is until now, it's not the exciting part, but from now is the exciting part, because we can now go back and test all of these different assumptions, different hypotheses that how vegetation water stress is related to mortality or wildfires, because now we have the data to do that, right? So that brings me to chapter 4, effects of vegetation water stress on wildfire occurrence. The motivation for this chapter is that weather-based metrics of vegetation water stress are currently used in the wildfire danger model. You know the one with Smoky Bear that used subjective relationship between light field moisture content and vegetation water stress. And the hypothesis here is that vegetation water stress beyond a threshold increases the odds of a fire. Before I went into this work, there was a lot of work already being done in this topic about vegetation water stress and wildfire occurrence. Here, for example, Chubiko et al. Show that as vegetation water stress increases, the number of fires increases on the y-axis here. But this is only from correlational evidence. This is just looking at where fires occurred and what was the vegetation water stress before that fire, right? And if you're like Dante again, you already know that correlation does not imply causation. And there's a small comic here to explain why that is. I'll give you a moment to read through it. Okay, so yeah, correlation does not imply causation, but how does this actually affect our own hypothesis of vegetation water stress effect on wildfire occurrence? Let's see that by using an example here. So on the left side is stressed vegetation, and on the right side is non-stressed vegetation. I'm simplifying here. It's not a binary term like that, but I'm simplifying here. And on the left side, in that ecosystem, there are also high winds, as an example, and there are no winds here. Now, if a fire occurs here, how do we tell if the fire occurred because the vegetation was stressed or because there were high winds over there? This is why I said that correlation does not imply causation, because other environmental metrics can be correlated to vegetation water stress, leading to incorrect inferences, right? And not just that, is this because of winds or because of vegetation water stress? What percentage of the wildfire occurrence probability is attributable to vegetation water stress versus other factors is also an unknown question, unknown as of now. So that is why we need to control for all of these different metrics and estimate the effect of vegetation water stress. How do we do that? In my lab, again, before we go into any particular solution, we take a step back and write every option one by one. I learned this from Dusty's lab. And the first option would be, in this case, to actually go to the field, light a fire everywhere, and see in which particular cases did it turn into a wildfire, right? You're already laughing, so you understand that this is impractical, unrealistic, illegal, and dangerous. So we did not do that. Instead, we relied on nature's own randomizer, lightning. Specifically, I analyzed where all lightning occurred. We are still in the same scale, California, where all lightning occurred, which is in purple, shown here, points, and where all lightning was was followed by a wildfire within 2 days. So that's shown in yellow. So this way we are able to estimate not just where there were fires, but also where there could have been fires, but there were no fires. I hope that makes sense. Associated with this, we also observed just before the lightning, where was the vegetation stressed and where was the vegetation not stressed. So these are the same points on the same day, and we are just seeing if the vegetation was stressed in one condition and not stressed in the other condition. Again, we cannot just correlate the blue dots to the yellow dots, because on these days, winds or some other factors could have been differing as well. So we need to control for all of these different metrics, environmental metrics, which is what I did to come up with comparable pairs. Here, that process is shown. On the x-axis is some environmental feature, let's say wind, and on the y-axis is another environmental feature. we map all the lightning events onto this feature space and calculate the covariate distance between every blue and brown pair, which is what is shown here. And what this gives us is that a sense of how different is this dry lightning event from this wet lightning event for all of these other covariates. And by running a global minimization algorithm, I can then come up with comparable pairs where the lightning event for the dry vegetation is as similar as possible to the lightning event at the wet vegetation. When I say as similar, I mean very similar location, very similar precipitation, meteorological metrics, very similar amount of fuel availability, and so on. Now that we have controlled for all of these different environmental variables, we can estimate vegetation water stress. And if you're already bored, just hold on. Now I will show you the result. So here is the effect of vegetation water stress on wildfire occurrence. And on the y-axis is the increase in the odds of a wildfire. Odds, in this case, you can translate that to probability as well, because there are very few positive wildfire events, positive events. Sorry. So what I show here is that when the vegetation is stressed, the odds of a fire increases by 1.8 times, controlled for all other different metrics. So I've already controlled for that, removed that effect out, and I'm claiming that the odds of a fire increases by 1.8 times when the vegetation is stressed. And earlier I mentioned that I'm simplifying a lot. Vegetation is not like a binary stress, no stress thing. So I went back and tested that again for different levels of difference in the stress between the dry lightning and the wet vegetation lightning pair. I show that the odds of a fire monotonically increases when the vegetation stress increases more. In fact, it's about the odds of a fire increases by 2 if the vegetation is very stressed as compared to the unstressed. And this is like the first evidence for vegetation water stress effects on wildfire occurrence controlled for all other environmentally varying factors. And if you're thinking about the implications of this work, I'd like to just ask you to hold on to that thought, because we'll come to the implications at the end of chapter 5, because both this and the next chapter are going to be on wildfire. The next chapter is going to be on wildfire burned area. And you can see that we are now towards the rightmost here. We are at the largest scale that I have studied. This is going to be across the whole Western US. The motivation for this is exactly the same. I copy pasted it. Weather-based metrics are being used for wildfire danger estimation. And the hypothesis here is that vegetation sensitivity to water stress regulates the increase in burned area under arid conditions. This same hypothesis is shown graphically here. Imagine there is some vegetation in high plant water sensitivity regions. If the climate dries, then the plants, all of them will also dry down because of high vegetation water stress. And if there is an ignition, it will lead to large burned area, right? On the other hand, if there is an ecosystem with low plant water sensitivity, for the same decline in climate aridity, only a few plants will dry, or qualitatively speaking, plants will dry less, leading to less wildfire burnt area. If you know the status quo is that there is no variation. Like we just say that meteorological estimates are informative of vegetation water stress. But I teased this in the introduction that they may be varying. But now that we have the data to test this, we can actually see if my hypothesis is true or not. And if it is true, to what an extent does it affect wildfire burned area. So I tested this hypothesis by first calculating plant water sensitivity. The way I did that is on the left side is light fuel moisture anomaly, again, vegetation water stress. On the right side is climate anomaly. It's a simple linear regression. And the M here, the slope, indicates plant water sensitivity. Because higher the slope, it means vegetation is more sensitive to climate. Lower slope, it's vice versa. Training this regression, calculating this regression in every pixel shows that there is indeed very high variation in plant water sensitivity. In green areas are the areas which have low sensitivity to climate anomalies, meaning even if the climate dries down a lot, the plants are able to maintain or only decrease slightly in terms of vegetation water. And in the pink regions like the Sierra Nevada, and Eastern Oregon, they have high plant water sensitivity, meaning if the climate dries down a little bit, the plants are not able to cope with that and dry down a lot. So this is the variation in plant water sensitivity, but this is still not the final step. We are still one step back. How does this affect burned area? And that's what we're going to see on this slide now. If I see only the ecosystems with who are least sensitive to climate anomalies, basically the regions with low plant water sensitivity, in those regions, burned area and atmospheric dryness have a slightly increasing relationship, meaning when the atmosphere dries, burned area increases by this amount. But comparing this to the most sensitive ecoregions, the pinkmost regions, we see that burned area increases by twice as fast. You see that this slope is much bigger than that slope. It's twice bigger than that. And these are only for these two, like the most severe ecosystems. But if I putting it all together now, if I show this in the same plot now, this slope is now the y-axis here. So this is being showed as burned area sensitivity to atmospheric dryness for the least plant water sensitive regions. If I pull in the pink regions, the regions with more slope, they're on the y-axis here. And if I do this for every other plant water sensitive regions, sure enough, they all follow an increasing trend. And this is the first evidence that plant water sensitivity has a direct regulating relationship on burned area sensitivity to atmospheric dryness. Okay. And this is not just an ecosystem property. This was all possible because of the data that we generated during all of these preceding chapters. And now we are able to actually give quantitative evidence of the strength of the relationship. And if you're thinking like Dante, if it is actually affecting you, or is it just an ecosystem property? The sad news is that it has likely already affected us in the past. And to understand that, let's first understand a big risk in wildfires called wildland-urban interface. And these are the regions where urban areas, like say houses here, are within wildland environments. Imagine like Los Altos Hills or Santa Cruz Mountains, or are at the fringes of an urban area. So let's say the edges of an urban environment here, near a wildland environment. And these areas pose high fire risk because of abundance of human-related activities here, which can cause ignitions, and there are wildlands which support that ignition to become burned areas. So what is the population growth like in these wildland-urban interfaces? I analyzed that, and I saw from literature that the wildland-urban interface, called WUI in short here, has increased by, has roughly doubled between 1990 to 2010 across the entire Western US. That was already known. It was not my contribution. But by splitting that wildland-urban interface into low, medium, high hazard regions, which I showed on the previous slide, based on the nonlinearity of this relationship, I can now test how much population grew in these different plant water sensitive regions of the wildland-urban interface. The good news is that low and medium hazard regions roughly track the same amount of population growth, but in the highest hazard regions of the wildland-urban interface, there was a 160% increase of population, which was disproportionate and is equivalent to 1.5 million people being added to the most hazardous regions of the wildland-urban interface in these 2 decades. So to answer Dante's question, it has already affected us in ways that we were not familiar with. because of this ecosystem property of plant water sensitivity. Coming back to this picture that I showed in the introduction, you remember this picture that I took at Yosemite while biking for different, which inspired and made me curious about this work. This same picture got highlighted on the cover of a journal, highlighting the importance of this work as well. And answering Dante's previous question about the implications of chapters 4 and 5, now that we have evidence that vegetation water stress increases the odds of a fire by 2, and the variance in vegetation water stress increases the sensitivity of burned area as well by 2, we think that this can improve wildfire danger estimates because now we have these maps of vegetation water stress, and we have given evidence of vegetation water stress effects on wildfire hazard. It may also improve public safety power shutoffs, because by looking at the risk profile, by looking at the probability of the increase in fire odds, the expected increase in fire odds, we might be able to target public safety power shutoffs better, as well as prescribed burn planning as well. So I'll leave this thesis outline. We took a journey across scales and across the whole scientific process about vegetation water stress and its effects on mortality and wildfires. And I'll take any questions if you have.
Questions?
Oliver.
Great job. My question is about the odds of the fire that increases sometimes 2. Can you explain what are the factors that lead to large? What are the dominant factors that lead to that?
Yeah, so, that's a great
Can
question.
you repeat the question for those of us who are on the internet?
Yeah, Peter, I'll do that. So the question from Oliver was that, although I show an effect of vegetation water stress on wildfire occurrence, what is the significant driving factor between for these big uncertainties? I think that, well, firstly, our estimate of vegetation water stress is itself imperfect. The maps that I showed, although I said it's like the most accurate, it is still about the explained variance is about 0.67. So there's still a lot of unexplained variance, which might be affecting the false positives or the true negatives while classifying lightning, which lead to wildfires. And the second one might also be just statistical. Less than 1% of lightning ignitions have caused wildfires in my data set. So there are very few true positive cases, meaning very few lightning events which led to fires. So there is limited ability for me to build these across different vegetation thresholds and test the statistical significance.
This is a good thing. You don't have all the
Yes, I do not mean to say that it's a bad thing. It's a good problem to have, I think. Yeah, Emily.
Great, Krishna. I had a question about chapter 5.
Mhm.
So I was curious where you have like the green and pink map. Did you have to account for essentially like anthropogenic effects on plants? For instance, like irrigated agriculture, like I see a lot of green dots in the Central Valley. Like, do you have to account for that?
That's a great question. Do we have to account for the fact that anthropogenic activities like irrigation affect this plant water sensitivity map? Well, I've tried my best to mask out such areas. So here, for example, I'm only showing shrubs, grasslands, and forests as predicted by the National Land Cover Database. But you can see that, yeah, there is still some residual coming in from the Central Valley, which seems to be less water sensitive, which kind of makes sense. They should not, or they're expected to not be sensitive to climate because they're like artificially being irrigated, right? So I still don't know why it's showing up so brightly green here, even though I masked it out, all the croplands out. Maybe if I use a land use map rather than a land cover map, where I know like what are actually artificially being irrigated and such things, these areas might get to completely masked out. But as of now, it's like all wild environments like shrublands, grasslands, and all
Oh,
this.
that makes sense. Thank you.
More questions? I couldn't have been so clear. Yes. Oliver again.
I could ask questions all day.
Want to be on my committee?
Please.
If you were an insurer, you were high-risk homes. But you were when you buy homes without insurance.
The question was, in these pink regions which have high plant water sensitivity and associated high burned area hazard, should I advise insurance companies to, I don't know, increase their premiums or not insure them at all? I'm going to shut up. I'm not going to claim that because we do not know. I'm showing here only one axis of wildfire hazard, which is like the sensitivity of burned area, right? But wildfire risk is impacted by many different things, not just plant water sensitivity, like fuel growth, like what's the human activity, like how much is the wildland urban interface expanding over there? What is the home hardening situation there? Are structures protected? So wildfire risk is not the y-axis here. And that's why I'm not able to claim to insurance companies to do either or the other. More research is needed for that.
A related question. So when you broke up the increase in the populations in low, medium, and high risk area, were you able to like look at the spatial distribution? Those here, like everything is aggregated, and so we don't have spatial information, but I guess you had access to that. So.
Yeah. So Paul is asking here is the population growth aggregated over these different hazard regions, but where are these actually occurring spatially, and can we learn something from that? And where they are occurring. I think we can learn. I have not done that yet. It might tell us, that investigation might tell us why this is occurring or the factors which are driving this kind of disproportionate population growth. But that's a very good suggestion. I've not done that yet. Yes, Ellie.
I have a question from the Zoom chat. Anakul Lakia, and I apologize if I mispronounced the name, says, "Hi Krishna, can you elaborate further on the applications of your work to prescribe burning? Also, can you comment on the vegetation stress and the recent Orange County fires going on?"
Okay. Thanks, Anukul, firstly, for coming to my talk. The first question was, how can this be used for prescribed burning? I think, so before the prescribed burn occurs in the state of California, they always have to take a measurement of the live fuel moisture before they can get an approval for the burn. So when they get the live fuel moisture content measurement, I think now we can take this result and say by how much are the odds of fire expected to decrease in that case, because it's a prescribed burn. And that might help make better strategies or better approval plans for prescribed burning, especially because it is so lacking in California. Second one is, how can you please repeat?
Yeah, can you comment on vegetation stress in the recent Orange
Oh,
County
yes.
fires going on?
I cannot comment, I'm sorry. I cannot like attribute every single fire to a specific cause. I mean, any fire to a specific cause. What I'm doing here is like aggregated analysis over vast time scales. So I actually don't know why that fire occurred. Yes, come.
Thanks for the great talk. I want to ask you, can your research now be used to help, for example, climate models and further expand on that?
So Tom is asking if my research can influence or influence the development of climate models. So within climate models, I mean, let's think about the Earth system as a whole first. Within that, there is like the climate piece, the ocean piece, and the land piece. Within the land piece, there are like dynamic vegetation models, which predict based on like climate forcings, how is the vegetation going to grow and change. I think that because wildfires are a significant effect on the land cover of a medium. For example, if there is there have been evidence where wildfire changes from the tree forest to a shrubland or a grassland. So because wildfires can affect land cover, I think that using vegetation water stress derived from observational evidence can improve those models. Yes. One last question, maybe, Derek.
Is there data available to expand this globally? We talked about in the class, a global map. Is this technique ready to be applied worldwide, in the next couple of years, or is it only the West has this sort of data that would be useful?
So Derek is asking if we can make vegetation water stress maps for the globe. That would be my dream. That would be the ultimate goal. I can make these maps even now globally, like the satellites go globally. The problem is that I'm hesitant to do that because a prediction is only as good as the validation data available to test it, right? And I'm very wary of giving just predictions without knowing what's the accuracy. 93% of global live fuel moisture content measurements are made in Western US alone. So the entire other part of this world only has 7% of the measurements. So it's a very unconstrained problem for data. And if there are like more measurements, or if the chapter 1 technique that I showed, the radars are installed in different areas, then we might be able to scale this globally. But others are trying to do this as well. I'm not the only one trying. Can I move on to acknowledgements?
One
Okay.
more, we have time for one more question, or do you want to?
9:58.
Okay,
one more question.
Yes.
In the microwave transmitter receiver setup, the receiver captures the line of sight microwave radiation rather than area. Could you please elaborate on the transmitter receiver setup to overcome this issue?
That's an excellent question. So the question is that the receiver gets a signal from the line of sight of the transmitter. Sorry, this is from chapter 1. And can this actually estimate the vegetation water in not just the line of sight, but in other surrounding areas as well, right? So we thought a lot about this. So first of all, the transmitter is not a directional transmitter. It has about 60-degree half lobe width on either side. So imagine that as not like an antenna, but like a lamp. It is like shooting microwaves this way. And the same with the receiver. The receiver is capturing microwaves this way. So we expect the radar amplitude to be reflective of a diamond-shaped transect of the land between those two antennas. But we have not actually like mapped the footprint of exactly how sharp that is. All right, thanks for all the questions. I'll just quickly go through some acknowledgements because this was not a single man journey. This was a collective effort. And I'd first like to thank my advisor, my guru, Alex. Alex, you've been so kind, so patient with me. And when I came to USA, I thought I wouldn't do PhD for sure because I thought people are just like PhD people. I had a stereotype are just on the whiteboard doing things which are not useful. That is not true. And I learned that from you to make research relevant to the outside world, to have applied research and impact-based research. So thanks for taking me on this journey. And I've said that I've called you my guru. For people who don't know, guru is like a Sanskrit word with two words. One, gu means darkness, and ru means the one who dispels. And Alex, you embody every sentiment of that word. You have trained me from someone who didn't even know how to read papers to actually step back and let me investigate my own hypotheses. So thanks for being the guru to my life. I'd also like to thank my committee, Noah, Dusty, Park, and Peter. Thanks for being such awesome research collaborators. Before, again, like few of you, I've read about you even before coming to Stanford, and it has been such an honor to get to work like the who's who of the research community. It's really a big honor to get to work with you. Noah, it's so awesome that you're still like so down to earth and humble. You correct my past tense to present tense mistakes in my papers. Dusty, I look at you as a friend first and then an advisor. You're so chill, probably the chillest person in Stanford. Thank you. Thank you for being the friend in my PhD journey. And Park, you too. Thanks for mentoring me and collaborating with me in all this research. And thanks to Peter too for chairing this committee. There's a blank there because I think I associate another scientist, Martha, as well, as somewhat informally in my committee. She's been a research collaborator all along. She's not on my committee because it's 2 a.m. in Australia right now. Thank you, Martha, for being an awesome research collaborator. Thanks to also super talented science outreach community of Stanford. I think Josie and Dee are not here. They're probably on camera. So I'll look at you and in the camera and really thank you for communicating my research, distilling it in such a neat and succinct way to explain the importance of my research. Fun fact, my parents never understand what I do unless they read your article. Thanks for writing such flawless science articles about my research.
My parents also.
Thank you to the amazingly helpful administrators of my department and my previous department. Haley, I did not have a photo of you, so that's Haley over there. Thank you for supporting me in my research, my field work, and my travel as well. Thank you to the remote sensing eco-hydrology group. You've been such awesome, again, science buddies. You've helped me even in my technical as well as non-technical stuff. Nathan, are you here? I don't know. Thanks for always being beside me. You have been like a window to American culture for me. You're the first person I met here. I'm trying to understand America as well as like things like, hey, Nathan, can I ask you, can I say this to an American? Like, how do you say this? The intricacies and the etiquette in America and the English here. Thanks for teaching me all of that. And Try Team. Thank you for being this vent of all the frustration that I have during my research and able to just blow it off during triathlon activities, fun as well as like social gatherings as well as workouts. You have such an like a concentrated, intense amount of happiness and joy and energy within you. I feel so nice and so happy that you have joined me on this journey. Thank you. And speaking of the triathlon team, Irene, the designer of Dante, needs to also be thanked. She never looks like this. She's only trying to imitate Dante in this. She's always full of positivity. And like, I don't know, like people look to coffee for a boost of energy. I look to Irene for a boost of morale. Thank you, Irene. And she's accepting freelance work if you want your own customized Dante in your own customized expressions. Thanks to another club I am also part of, the Talk of the Farm. It's a speaking club. All of you are on camera, so I'll look at you. Thank you for helping me communicate, be a better communicator and a better leader. And for those of you who felt that my talk was good, it is only because of Talk of the Farm Club. If you think my talk was bad, imagine how worse it was for this club. I'd like to, of course, thank my family, Amma, Appa, Ajja, my brother, Anna, Suma, and Harshita. You have made so many sacrifices for me. I cannot even count. Thank you for that. Here I'm teaching my mom how to do a video call for the first time. She's so excited. Gosh, yeah, you're my true heroes. You've taught me so much and sacrificed so much for me. Thank you for letting me do this and giving me this opportunity. The last thing I would like to share is that before coming to Stanford, I was a field engineer as an oil and gas field engineer. Behind me here is it's a completion rig where I'm doing some operation on the well. And on the other side of this photo is my utility truck and a small van here with 4 armed guards to protect me. Imagine that for a second. I'm at a place and the nature of my work was such that all the local people did not like me there. And because of that, my company felt it prudent to guard me from these dangers. Going from that kind of a situation where everybody around me disliked me to such an extent that it can become a life threat, to a region, to a place where everybody around me loves and cares for me and is deeply rooted in my, deeply invested in my personal as well as professional growth. I cannot explain how happy I am. It is maybe some magic, some almighty or some hidden force or luck which brought me from that kind of a world to a world where everybody loves me. I'm really happy. Thank you.
Thank you, Krishna, and thank you, everyone. We will reconvene in 10 minutes, the committee.
People can